Welcome to Kinetics and Thermodynamics Lecture A. Today I'd like to talk to you about collision theory, factors that affect the rate of a reaction, and potential energy diagrams. So let's start off with collision theory. What we know is that when reactions occur, particles must collide. If I'm going to try to make ammonia, I know I'm going to need some nitrogen and I'm going to need some hydrogen. But in order to get that to occur, if I take a look at my balanced equation, I'm going to need to do a couple of things. I'm going to need to break old bonds. So nitrogen usually looks like this right here. It has 5 valence electrons and a triple covalent bond. And each hydrogen has 1 valence electron and a single covalent bond. And our ammonia looks like this right here. It ends up being in that pyramidal shape like that. And of course I have 2 of them. So there's no way I'm going to go from this on the left of the arrow to this on the right of the arrow in one shot. So clearly, of course, our old bonds have to be broken first. So I add energy and I break these old bonds. So say I get my triple bond between the nitrogen broken, and I get my 3 single bonds between the nitrogen and hydrogen broken as well. Again, this is not going to happen in one shot. So far, I've already done 6 steps. I've broken a triple covalent bond, and I've broken 3 single covalent bonds. And so what do I know has to happen? These particles are swimming around in the beaker together, so how are we going to get them to connect? Somehow they have to collide. And so I know that a nitrogen has to collide with a hydrogen, and I can maybe get an NH out of that. And then that NH has to collide with another H, and I might be able to get an NH2. And then that NH2 needs to collide with another H to get NH3. So you can imagine it's a series of 2 particle collisions that end up causing new bonds to be formed. So we can get these particles to collide, but it's possible that they might not react together, because when they do collide, the collision between these 2 particles has to be effective. In other words, I can't have some little old lady car crash in the Stop and Shop parking lot, a little fender bender. No, I have to have enough energy to be able to break old bonds, and I need to be able to form new bonds by having the particles lined up the right way. So an effective collision occurs when we have everybody lined up the right way and when we have enough kinetic energy. So they have to be lined up and they have to hit hard. So let's take a look at an example of what an effective collision might be. If you look at this reaction between 2 particles, I guess we'll call them brono. If I've got 2 bronos that are trying to collide and cause the bromine to break off and bond together, we know that we can get an effective collision, but somehow, some way, we have to get the bromines lined up because they are the effective part of that collision. So you see that in this initial scenario, if they are going to hit each other along these lines like this so that these bromines collide, then the bromine can break off and that's going to be a successful collision. Whereas I look at letter B, again, if I've got the brono going end to end so that the bromines collide together, then it can break off like this, and this would be a successful collision. But if those molecules are floating around in space, if they happen to flip over and it happens to be the oxygen ends that connect, this reaction isn't going to happen. So this is an example of how alignment affects the success of a collision. So this would be considered as an unsuccessful collision. So regarding the amount of energy we have to add to break old bonds, so this is going back, when bonds are broken, energy must be added. And so that's the BA of BARF. Remember that it's bonds are broken, energy must be added, and energy is released when bonds are formed. So the amount of energy that we have to add to break old bonds is referred to as activation energy, and it is often abbreviated with this E sub A, like this. And it is the energy that we have to add to break old bonds. So let's take a look at a potential energy diagram that you see down here at the bottom. What I see, the x-axis is labeled as reaction progress. Technically speaking, it's time. At the beginning of time, I always have the reactants in a chemical equation, and at the end of time, I have the products in a chemical equation. So it would make sense that as the reaction progresses, I go from reactants to products, and then we measure the potential energy as a result of those changes. So taking a look at the very beginning here, I have my reactants. Reactants, we can see there, have kind of a low potential energy, and you'll see the particle diagrams around the curve indicate that some old bonds are being broken. So the activation energy that we speak of is from reactants to the top of the hill. Reactants to the top of the hill is going to be my activation energy. So in this specific example, from reactants to the top of the hill, my activation energy is 120. So when I have all of my old bonds broken, you will see that we are at the highest energy situation. This high energy situation is not stable. High energy is the worst. It's not stable at all. All of our old bonds are broken. We've added a whole ton of energy to the system, but our new bonds haven't been formed yet, and we are not able to release that extra energy. So what we refer to that spot at the top of the hill is called the activated complex. So to recap activation energy, if I have to look at it on a graph, it is from reactants to the hilltop. And the energy of our activated complex is the hilltop. So I can see that the energy of my activated complex there in this graph is 120. So as we look at activation energy, I can't help but think of this particular analogy where I've got to take this boulder and push it up over the hill. Clearly, it takes a lot of energy on my behalf to make that happen. And you can only imagine while I'm pushing this boulder up the hill, the whole time I'm wishing, gosh, I wish this hill were a little bit lower. If there was a way I could make the hill only this high, I could push that boulder over that teeny tiny little molehill really easy. So you can imagine, if I have that high activation energy, it takes a long time to be able to get that reaction to occur. Whereas if my hilltop is a little bit lower, my reaction can be a little bit faster. So that's our takeaway right here. If we have a lower activation energy, we can get a faster reaction. So how on earth, what can I do to a reaction to lower the activation energy? That is the burning question right there. How can I lower the required activation energy? What's required is required. How can I take that hill and chop it down a bit? We will answer that question as time goes by. What we know is, as we said, reactions happen when particles collide. They have to have the sufficient amount of energy and they have to have the correct orientation. So that's our big takeaway from collision theory. So how can we make that reaction faster? Anything that's going to give us collisions that occur more often, collisions that occur with harder crashes, collisions that are more efficient in a certain amount of time will make our reaction rate increase. So I often think about car crashes, like how could we increase car crashes? And I'm not talking, like I said, little old lady fender benders in the Stop and Shop parking lot. We're talking about car totaling crashes. Not that I advocate for that or anything, but here we go. First of all, there are some people that are just have a higher rate of having car crashes than others. You heard me say little old ladies in the parking lot at Stop and Shop. It's just their very nature. The very nature of reactants in a chemical change sometimes gives the reaction, makes it fast, sometimes makes it slow. The reaction that I started off today with, where I had to break a triple covalent bond, and then I had to break 3 single covalent bonds before we could even start collisions, is a very slow reaction. So when I have lots of multiple covalent bonds that have to be broken, these are really slow reactions because it requires a lot of energy. However, if I have aqueous ionic reactants, say for example, I had silver nitrate as an aqueous solution and sodium chloride as an aqueous solution, what do we know? These compounds are ionic. They have a cation, they have an anion. And because they are aqueous, we know their ions have been dissociated. So in a funny kind of way, these compounds already have their old bonds broken. So they're already 6 steps ahead of the reaction that forms ammonia. So these happen to be faster reactions. Next, going back to our car crash analogy, I often think of, am I going to have more propensity to have car crashes on the George Washington Bridge on a Friday of a holiday weekend or in Montana? I'm thinking probably choice A, and why is that? Most likely because of traffic. It would make sense that if I have an increased concentration of my aqueous reactants or a higher pressure of my gases, that means I'm going to have more traffic, and of course I'm going to have more collisions. Next, so this happens to work for aqueous reactants, it happens to work for gaseous reactants. It works for AQ and it works for G. So now how about if I have a solid reactant? If I have a solid reactant, I want to consider its surface area. If I have a big chunk of zinc that I'm going to put in hydrochloric acid, as opposed to zinc powder that I'm going to put in hydrochloric acid, what do you think is going to react faster? Of course, it's going to be that zinc powder that reacts faster, simply because I have a higher surface area that allows for that solid to connect with the hydrochloric acid much more often, much more frequently. Then last but not least, we got more hotter, more faster. Yep, temperature. There we go, I can type. Temperature, more hotter, more faster. So of course, if I'm speeding, that's what temperature is in the chemical world, right? If I'm speeding, if I'm going 85 miles an hour, there's a better chance I'm going to get into a big, bad car crash than if I'm going 55 miles an hour. So higher temperature means higher kinetic energy, and that means more collisions. Now, last but not least, what can we do just as a matter of not manipulating any of the reactants? What can we do to reduce that activation energy? So of course this time my boulder is in a wheelbarrow. The wheelbarrow is of no circumstance. It's the height of the hill that makes a difference. I can add a catalyst. And how does that catalyst work? Maybe you've heard of this in your bio classes, where you might have recalled that enzymes are catalysts. Catalysts work by taking the height of that hill. If you recall correctly, from reactants to the top of the hill is our activation energy. So without a catalyst, I've got my activation energy is as big as that blue section. But with a catalyst, you can see I can greatly reduce that activation energy. And so it essentially knocks down the height of that hill, if you will. So a catalyst works because it reduces the required activation energy for the reaction to get started. As we mentioned before, kind of channeling back your inner bio student, we know that all enzymes are catalysts, and you might remember being taught about the enzyme substrate complex. So enzymes are specific to their substrate. You might remember the lock and key model, so they are very specific to what they work on. And of course, we know that they are catalysts and they work by reducing the activation energy required by the substrate to undergo its chemical change. So now, I started off the day showing you that reactions took place in a series of steps, and that is 100% true. When I consider I can have a big chemical reaction that is the sum of two or more little chemical reactions, you know that a reaction takes place in a series of steps. So now let's take a look at what we have here. If we look at our overall reaction, you can see that it takes place in 2 steps. So our first step, we had an NO2 plus an NO2. And they underwent a series of 2 particle collisions. And you can see that they made NO3 and NO as a result. Then in our second step, we looped that NO3 around to become a reactant. And that NO3 became a reactant with another substance, carbon monoxide. And you can see as a result, we got an NO2 and a CO2. So let's take a look at what results. You can see my cancellations, and we've done this before when we did Hess's law. But what we see is there's 2 things that are being canceled. We have NO2 that is being canceled. And we also have NO3 that is being canceled. Now you heard me say in words what I was doing to the NO3. You can see that it appeared as a product, and then in a later step, I looped it around and it became a reactant. As a result, NO3 is referred to as an intermediate. And we said, how do I know it's an intermediate? Because in an early step, it appears as a product. And then in a later step, it appears as a reactant. Whereas now let's take a look at NO2. What I can see is that my NO2 cancels out, but in the early step, it was a reactant. And then in the later step, it is a product. So this is a catalyst. And it fits the definition of what an enzyme is. If you remember, the lock and key model of enzyme action indicates, of course, you don't use a key and a lock only once. You use it multiple times. It's reusable. So you'll notice that it fits that definition because in our mechanism, it appears as a reactant first. And it appears to be consumed, but then later it's regenerated as a product so that if necessary, it could be reused as a catalyst in the future. So we can see that even though NO2 and NO3 were both canceled for our overall reaction, they were not created equally. So now here you have intermediate and catalyst are defined for you right here. In our potential energy diagrams, what we know is if I start off with a set of axes, we know that our x-axis is time or reaction progress, or sometimes it's called reaction coordinate. And we know that we have the reactants at the beginning and we have the products at the end. And that our y-axis is meant to measure potential energy. And that's usually in kilojoules. So what happens is our reactants generally have a certain amount of potential energy stored in their chemical bonds. And so as a result, our reactants, we will usually get like a flat line at the beginning of any potential energy diagram. Then we know our old bonds are broken. Our old bonds are broken because we add energy to break those old bonds. And that is our activation energy, as we mentioned before. Our activated complex is our highest energy situation overall, and it sits right there at the top of that hill. We've taken the reactants and we've broken all of their old bonds. Then what do we know? That activated complex is going to start coming together and forming the bonds for products. And so as I take a look here, I can start forming the bonds, and we know that's going to involve a release in energy, and then we can get our products from there. So then our products can be right here. And so what do I know? As we said, our activated complex is going to break down, form the products, and this is when new bonds are formed, energy is released. So we know that this is bonds are broken, energy is added, and this is energy is released when bonds are formed. And what do we notice here? I look at where my products are. It is that second plateau. And what I notice here is that I have, compared to the reactants, this is a lower number. Reactants are a higher number. And so what is going to occur? My delta H, or my enthalpy, is calculated by doing heat of the products, or energy of the products, minus energy of the reactants. And if I take a low number and subtract a high number, I'm going to get a negative value for delta H. So you can see the example that I drew for you, free of charge in table I, indicates a negative delta H is an exothermic reaction. So the good news is that we can take a quick look at the exothermic reaction here. What do I see here? If I had to identify all the parts of a potential energy diagram, I could do it pretty easily. I have my reactants. My reactants are going to be that first plateau. Reactants are the first plateau. So if I had to characterize it in words, that's how I would do it. From reactants to the top of the hill, I have here, reactants to the top of the hill is my activation energy. Activation energy, as we said, is from reactants to the top of the hill. I have my activated complex. My activated complex is the hilltop. Activated complex right there is our hilltop. And I can see that I'm going to start forming new bonds here. Energy is released when I start forming my new bonds. And I have my energy of my products. Here is my last plateau. So what do I know here? The green here is our energy released when new bonds are formed. And my last plateau is my energy of my products. My energy of my products in this particular situation, you can see, is lower than my energy of my reactants. So how do I calculate my delta H, or my enthalpy? I took the energy of the products, which is 30 kilojoules, and I subtracted the energy of my reactants, which is 70 kilojoules, and that's how I got my delta H. How do I get my activation energy? I take the difference between the energy of the reactants, which is 70, and the energy of the activated complex, or again, from reactants to the hilltop. My energy from reactants to the hilltop, I can easily see, is the difference between 70 and 150, and that is 80 kilojoules. And of course, activation energy is always the energy added, so it's always endothermic, and so the sign there doesn't really matter. The energy of our reactants, that first plateau, if I had to put a number on it, it would be 70 kilojoules, and I just read that from the first plateau. And the energy of my products, I would again read that from simply my second plateau, and that would be 30 kilojoules. I talked about how to calculate enthalpy. We can also read this reaction in reverse. If I had to read this reaction in reverse, the orange would be my reactants, and the pink would be my products. And my activation energy would still be from reactants to the top of the hill. So my activation energy of my reverse reaction, should I need it, would be the difference between 30 and 150 would be 120 kilojoules. So you can see that these graphs can be read numerically speaking. So we start off high, get low, and that's a good example of an exothermic potential energy diagram. And once we know one thing one way, we can know the exact opposite is true. I still have my first plateau. 60 is my reactants. So my energy of my reactants is 60 kilojoules. My activation energy is still from reactants to the hilltop. From reactants to the hilltop, I go. The difference between 60 and 130 is 70 kilojoules. The energy of my activated complex, I can read from my graph directly, is 130. My delta H is the difference between the two plateaus, the difference between the two flat lines, but I have to do it in a specific order. I have to go right to left. So it's going to be the difference, 110 minus 60, so my delta H here is going to be a positive 50 kilojoules, and as we know, that is indicative of an endothermic reaction. If I had to read the activation energy of my reverse reaction, I can see that my reactants would be here, top of the hill would be here, and I could see that the activation energy of my reverse reaction here might be 20 kilojoules. I can see that if I embed my energy term within my reaction, as we recall, the energy term goes on the left-hand side of any endothermic reaction. So now, how would this diagram play out if we added a catalyst? What do we know? I was trying to push the boulder up the hill, and I was really hoping that the height of the hill could be reduced. So if I add that catalyst, this is going to make the difference right here. Height of my hill is just going to be a little bit lower. So if I look at that same potential energy diagram, if I add a catalyst, I can see what gets affected. Does the energy of my reactants get affected if I add a catalyst? And the answer is no. Does the energy of my products get affected if I add a catalyst? And the answer is no. Does my enthalpy of my reaction get affected if I add a catalyst? And the answer is no. Does my activation energy get affected if I add a catalyst? From reactants to the hilltop, if the hilltop is now lowered, it most certainly will get affected with a catalyst. Is the energy of my activated complex affected by adding a catalyst? And the answer is yes, of course. Is the activation energy of my reverse reaction affected by adding a catalyst? Of course, I have to go to the top of the hill. So anything that would normally go to the hilltop is going to get affected if I add a catalyst. And so once we know one thing one way, the exact opposite is true. If we take a look at a exothermic with a catalyst, same thing we can see. Reactants unaffected, products unaffected, delta H unaffected. Activation energy goes to the top of the hill, that's affected. Activated complex goes to the top of the hill, that's affected. Activation energy of the reverse reaction goes to the top of the hill, that's affected as well. That is all I have for you for Kinetics and Thermodynamics Lecture A. I hope you enjoyed it and have a great day.